Imagine taking this beautifully machined, really high-end desk ornament.
Like a shiny metal cone, right?
Yeah, exactly. A
Yeah.
tiny gold and silver metallic cone. Now imagine taking that, loading it into a compressed air cannon, and just firing it into a wall at like 4 times the speed of sound.
Which is just a wild visual.
It really is. And now imagine doing that to safeguard a $1 billion interplanetary mission, because that's the exact scenario we are unpacking for you today. So welcome to the deep dive. I'm your host.
And I'm your resident space tech expert here to help, make sense of all the engineering madness.
Right. And today's mission for this deep dive is to explore this really fascinating publication from May 2026. It was released by the European Space Agency via techno-science.net, and the title just totally sets the stage. It's called "This is Not a Toy, This is a Tiny Martian Spaceship."
Which is such a great hook. I mean, it perfectly captures this concept of asymmetric engineering. Because when you think about conquering space, you assume it's all massive rockets and giant imposing machinery.
Yeah, Saturn V kind of stuff.
Exactly. But this ESA data forces us to look at these microscopic, incredibly violent details that actually dictate whether a mission succeeds or fails, long before the rocket ever leaves the pad.
And the visual they provided with this press release is just, well, it's honestly entirely disarming. So for you listening, picture this tiny, blocky, almost cute toy-like robot standing on a little patch of red sand, and right next to it is that little metallic cone I mentioned.
Right, the one that looks like a heavy Christmas tree ornament.
Yes, it's only about 7.5 centimeters in diameter, but the crazy part is that specific cone in the photo had literally just survived being blasted out of a supersonic gas cannon.
Yeah, they really put those things through the ringer.
So let's talk about the mechanics of this testing lab, because the metrics are, they're just difficult to wrap your head around. They built 20 of these miniature capsules, right?
20 of them.
And they fired them at 4,200 kilometers per hour. And the sudden deceleration subjected these little capsules to nearly 17,000 Gs.
Which, just to emphasize, is the critical data point of the entire experiment. 17,000 times Earth's gravitational acceleration. And that's applied in just a fraction of a millisecond.
I looked at that number and I really had to recalibrate my understanding of physics, because 17,000 Gs isn't just a heavy impact.
It's totally destructive.
Right. If you take standard terrestrial electronics, like, say, the telemetry hardware in a commercial jet or the smartphone in your pocket, and you hit it with 17,000 Gs, you don't just crack the screen.
Oh no, the whole thing just disintegrates. The internal solder joints shear instantly, the silicon chips fracture, all the battery layers crush into each other. Basically, the entire device just pulverizes itself internally.
It's like putting a smartphone on an anvil and hitting it with a high-speed freight train. So how does ESA build a 7.5 centimeter capsule that actually survives that level of kinetic trauma without just, becoming a solid lump of steel?
Well, it all comes down to structural geometry and some really clever internal material science. Because you can't just slap a thicker outer shell on it. The kinetic energy has to go somewhere, right? The shock waves just travel straight through the metal.
Oh, I see. So a thicker wall doesn't stop the inside from shaking itself apart.
Exactly. So to protect the internal volume, engineers rely on highly specialized potting compounds. What they do is they take all the internal electronic components and they completely encapsulate them in this really rigid epoxy resin.
Wait, so they just fill up all the empty space inside the capsule with essentially advanced glue?
Basically, yeah. By filling every single microscopic air gap with a resin that closely matches the density of the electronic components, you prevent the individual parts from moving independently.
Oh, wow.
Yeah, so if everything inside the capsule accelerates and decelerates as one single solid mass, those fragile wire bonds and silicon wafers, they don't shear off. They're locked in place. The kinetic shock wave just passes through the entire block uniformly.
Okay, that makes a ton of sense. You eliminate the internal rattling, so the delicate parts essentially become part of a single solid structure.
Right.
But, that brings up the overarching paradox of this entire ESA project. We're looking at extreme shock absorption and aerodynamic survival on Earth, but we aren't building a deep space kinetic weapon.
No, we definitely aren't.
We're building a transport vehicle for Mars, so why simulate 17,000 Gs of impact force for a spacecraft that's, well, supposed to use parachutes?
That is the million-dollar question. And to understand the necessity of this violent cannon test, we really have to look closely at the fluid dynamics of the Martian atmosphere.
Okay.
Because when a spacecraft actually arrives at Mars, it's carrying a staggering amount of kinetic energy. We're talking about approaching the planet at speeds exceeding 20,000 kilometers per hour.
Right.
And from the exact moment it hits the upper atmospheric boundary, it has less than 8 minutes to bleed off almost all of that velocity so the parachutes can actually safely deploy.
Right. And if you follow space news, you're probably familiar with that concept, the whole 7 minutes of terror thing.
Exactly, yeah.
But the aerodynamic profile that the ESA engineers are dealing with here is heavily dictated by the fact that the Martian atmosphere is just incredibly tenuous. I mean, it's roughly 100 times less dense than Earth's.
Right. And what's fascinating here is that this creates a massive, totally contradictory engineering problem. It is thick enough to generate a hypersonic shock wave, which compresses the carbon dioxide gas right in front of the heat shield and creates this blinding plasma layer that exceeds 1,500 degrees Celsius.
Wow.
But because it's so incredibly thin, it doesn't provide enough aerodynamic drag to easily slow down a heavy, multi-ton spacecraft.
So you're basically plunging into an environment that is perfectly designed to melt you, but stubbornly refuses to act like a brake.
Precisely. I mean, think about it like this. If you land on the moon, there is zero atmosphere, so you completely ignore aerodynamics and just use retro rockets to decelerate.
Right. Just blast your way down.
Yeah. And if you land on Earth, the atmosphere is incredibly dense, so you can use friction and parachutes with tremendous efficiency. But Mars sits in this frustrating, deadly middle ground. To force that thin atmosphere to slow the craft down from 20,000 kilometers per hour, you have to hit the air at a very precise, steep angle.
And that's where the G-forces come in.
Exactly. That violent braking process subjects the full-size craft to roughly 15 to 20 Gs of continuous acceleration.
Okay, so I'm looking at these two very different scenarios here. We have this 1,500-degree, 20G, 8-minute terrifying descent into Mars on one hand.
Yeah.
And on the other hand, we have ESA firing a baseball-sized metal cone out of a literal cannon at Mach 4 to produce a 17,000 G impact that lasts like a fraction of a second. How does the Earthbound cannon test actually translate to the Martian ascent? They seem like totally different physics problems.
Structurally, they are.
Yeah.
But aerodynamically, the cannon provides something you simply cannot get in a standard wind tunnel.
Oh.
Yeah. Because we can't build a vacuum chamber large enough to perfectly replicate the Martian atmosphere at 20,000 kilometers per hour for an object the size of a car. Standard wind tunnels work by bringing the air to a stationary model.
Right, you just blow fast air over a static shape.
Right.
Yeah.
But by using these hypersonic gas cannons, ESA is injecting the model into the air dynamically. It perfectly simulates the transient aerodynamic forces. So it shows them exactly how the shockwave forms, how the pressure builds on the heat shield, and how the craft naturally behaves in a rapidly compressing fluid medium.
Okay. And this is where the ESA publication gets incredibly technical and honestly quite brilliant. Because those 27.5 centimeter metal cones, they aren't just solid dummies.
No, not at all.
They are packed with delicate electronic circuits and microsensors. They actually shot a fully functioning, miniaturized telemetry computer out of a cannon at Mach 4 just so it could record its own flight.
Which is exactly why that epoxy potting process we discussed earlier is so vital. If we connect this to the bigger picture, in that tiny fraction of a second that the capsule's flying through the air, those internal sensors are operating furiously. They have massive sampling rates.
What are they measuring exactly?
They're measuring high-frequency vibration, microscopic pressure fluctuations across the hull, and dynamic heat transfer.
But, okay, why 20 of them? If they just wanted to prove the sensors could survive the 17,000 Gs and, record the pressure wave, they could have done it in 2 or 3 shots. Shooting 20 successive models suggests they are iterating on a design. Like they're looking for something highly specific.
You're spot on. They're actively fine-tuning the capsule's static stability. Specifically, they're trying to nail down the exact center of gravity relative to the center of pressure. Because when an object hits a fluid medium at hypersonic speeds, the atmosphere acts almost like a solid brick wall.
Right.
So you have to ensure that the aerodynamic sources naturally correct any deviation in the flight path.
Oh, so it's essentially the physics of throwing a heavy-tipped dart.
Exactly.
Like if you throw a plain wooden stick, it just tumbles end over end because the weight is distributed evenly. But if you put a dense metal weight at the very front of a dart, the center of gravity is pulled far ahead of the aerodynamic center of pressure. So even if you throw it awkwardly, the air resistance on the lighter tail section automatically forces the heavy tip to point forward.
That is the perfect analogy. And on Mars, that self-correcting alignment is literally a matter of life and death. Because at 20,000 kilometers per hour, surrounded by a 1500-degree plasma field. The heat shield on the front of the capsule is the only thing preventing total structural failure.
Right.
So if the center of gravity is off by a millimeter, the capsule becomes statically unstable. It begins to wobble. And if it wobbles too far, it exposes the unshielded top side of the spacecraft to the hypersonic plasma.
And without the thermal protection system there, the back of the spacecraft just vaporizes almost instantaneously. Instantaneously. Yes. So these highly instrumented supersonic cannon shots on Earth are providing the essential ground truth data. I mean, engineers can run fluid dynamics simulations on supercomputers for years, but eventually you have to validate the math physically.
You actually have to shoot it.
Right. These tiny capsules confirm the exact weight distribution, the specific geometry of the cone, and the exact angle of the stabilization fins required to guarantee the real craft will not flip over during aero capture.
So we have this meticulous, asymmetric engineering process going on. We are massively over-engineering a tiny capsule to survive a 17,000 G impact on Earth, just so we can confidently survive a 20 G aerodynamic deceleration on Mars.
Correct.
And here's the catch. A 7.5 centimeter capsule, no matter how perfectly balanced it is, has virtually zero payload capacity.
Obviously, yeah.
You can't fit meaningful scientific instruments in a tiny metal cone. This has to be a scale model for a much larger, much heavier architecture. It is. All of this aerodynamic fine-tuning is dedicated to protecting one very specific, very heavy piece of hardware, and that is the Rosalind Franklin rover, which is the centerpiece of the ExoMars mission scheduled for 2028.
Okay, yes. And I was looking at the schematics for the Rosalind Franklin rover in this ESA release, and what immediately stood out to me wasn't the camera array or the spectrometer, it was the drill.
Yes, the drill is the main event.
They are dedicating a massive amount of weight and power to this highly advanced drill designed to dig up to 2 meters deep into the Martian soil. And, my immediate thought was, why are we suddenly trying to dig a 6-foot hole on a planet where we still have millions of square miles of completely unexplored surface? Like, what is the strategic value of going down?
The strategic value is entirely driven by the search for ancient extraterrestrial life. You see, the immediate surface of Mars is, for all intents and purposes, a sterilized wasteland.
Right, because of the atmosphere.
Exactly. Because we established earlier that the Martian atmosphere is incredibly thin, it completely lacks a robust ozone layer or a global magnetic field. So this means the surface is constantly bombarded by harsh ultraviolet and cosmic ionizing radiation.
So any organic molecules or, complex biological structures that might have existed on the surface millions of years ago, they would have been completely broken down and destroyed by now.
Precisely. The surface radiation environment, combined with some really highly reactive chemicals in the dust, like perchlorates, it basically acts as a powerful bleach.
Okay.
So if you actually want to find pristine biomarkers, the chemical signatures of ancient biological activity, you have to get below that irradiated oxidized zone.
Oh, so previous rovers that just scraped the top few centimeters were essentially analyzing sterilized dirt.
Pretty much, yeah.
But by driving a drill 2 meters into the crust, the Rosalind Franklin will be accessing soil samples that have been shielded from cosmic radiation for potentially billions of years.
Exactly. It is arguably our best chance at finding intact organic molecules that could definitively prove Mars once harbored life.
Right.
But, and this is the kicker, you cannot deliver a heavy mechanical drill system to the surface if you don't perfectly master the aerodynamic deceleration.
Because of the weight.
Right. The immense weight of that drill drastically shifts the center of gravity of the entry capsule, which brings us right back to why ESA is firing those miniature models out of cannons today.
Wow.
The math has to be absolutely perfect, or that drill never even reaches the ground.
It is just a stunning chain of cause and effect. So what this means for you listening is that the grandest human endeavor, like the multi-billion-dollar search for ancient biology on another world, relies entirely on whether some engineer properly accounted for a millimeter shift in the center of gravity on a little baseball-sized test model in a lab somewhere.
Yes.
Because if that math is wrong, the capsule wobbles, the heat shield fails, and the Rosalind Franklin just burns up in the Martian sky.
The margin for error is effectively zero. Every single phase of that descent must be mastered perfectly. The initial entry angle, the plasma friction, the hypersonic drag, the parachute deployment, and achieving that absolute mastery requires uncompromising physical validation right here on Earth.
It really makes you appreciate the invisible layers of problem solving happening behind the scenes. But, looking at the sheer scale of the engineering required just to protect this one singular heavy rover, It highlights a really fascinating technological paradox in this ESA data.
This raises an important question, actually. What paradox do you mean?
Well, the entire purpose of this compressed air cannon experiment was to test the aerodynamics for a massive, delicate payload, right?
Right.
But in the process of running that test, ESA accidentally proved something else entirely. They proved that with modern potting compounds and rigid geometry, they can build highly advanced, miniaturized sensors that comfortably survive 17,000 Gs of raw impact force.
Huh. They essentially built an indestructible telemetry package.
Exactly. So if we have electronics that are that cheap, that small, and that physically robust, why are we still relying on the old paradigm of sending one giant fragile rover to slowly crawl across a few meters of sand every day? Like, if the sensors can survive a 17,000 G impact, why are we building parachutes at all?
Oh, wow. That is a phenomenal pivot in perspective. You're looking past the test itself and analyzing the implications of the hardware. Because as microelectromechanical systems, MEMS technology become increasingly sophisticated, the requirement for massive soft landing rovers might actually become completely obsolete for certain types of planetary science.
Right. We could transition from like a sniper rifle approach to a shotgun approach. Instead of spending billions meticulously balancing a massive heat shield for one delicate drill, we could manufacture 10,000 of these 7.5 centimeter completely indestructible sensor pods.
Oh, I see where you're going with this. You load them into an orbital dispenser, you simply drop them. You don't need complex aerosols or parachutes. You literally just let them hit the Martian surface at terminal velocity. They handle the kinetic shock without an issue because they are literally designed to survive 17,000 Gs.
Exactly.
And suddenly, instead of having one rover localized in a single crater, you have this massive decentralized swarm of tiny explorers gathering atmospheric pressure, seismic data, and temperature readings across an entire hemisphere of the planet simultaneously.
It completely inverts the engineering problem. And instead of fighting the hostile physics of planetary entry, you just build technology that ignores it. You use the brute force of the impact as your actual landing mechanism.
That's a brilliant thought.
Right. The very thing they designed as a disposable test model could actually be the blueprint for the next century of interplanetary exploration.
It's a highly compelling concept, and I think it proves that sometimes the most profound breakthroughs don't actually come from the primary objective of an experiment. They come from the extreme methods we invent just to run the test in the first place.
A completely decentralized, indestructible swarm of Martian sensors. I think that is the absolute perfect concept to leave you on today. We've explored the massive physical forces and the microscopic engineering tolerances that define our journey to other worlds. We want to thank you for joining us on this deep dive. Keep questioning the scale of how we explore, and never forget to look closely at the violently extreme details that make it all possible. Until next time.